That's an old commercial. Anyways, today we're doing introduction of circles, and we continue on this theme of answering timeless questions that have preoccupied humans for 4,000 years or more. So let's go back to our little pizza, and this time let's make it, say, it has a radius 5 inches. In other words, from here to the edge, it's 5 inches, so maybe there's 3 inches there and there's another inch there. More or less, 1, 2, 3, 4, 5. Now the question that has been asked for thousands of years is, if you've got a 5-inch circle, how many square inches can you get out of it? If you were to cut this pizza up into little square inches like this, how many of them would you get? That's an area question, and it's been asked forever. If you were to be alive, say, 4,000 years ago, and you had no tools at your disposal, for example, no Google, there was no Yahoo, Ask, there was nothing like that, there's no Twitter, how would you tackle this question? The reason it's nice to pose it that way is because we weren't alive 4,000 years ago. For many of us, we may be asking this question for the very, very first time. Maybe you're eating a pizza at home or something, and you got a lot of little kids and you want to cut up into tiny pieces, so you want to know how many pieces you can get. Whatever the case may be, let's look at it as if it was fresh to us, if it was a brand new question for us. How many square inches can we get out of it? That's a nice way, I think, to look at it. Let's start off fresh. Okay, we're square versions. We've never seen this question before. One silly little way to do it would be to take the circle and start, slicing it up, just with almost no special skills. Just start slicing, just count. How many squares do you get? Here, 1, 2, 3, 4, 5. So this is radius 5, so let's just start counting. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe you can go a little more, but it's kind of dubious here because part of the square is not contained, so I'll just stop there. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I'm nervous when I do this because part of it is sticking out. 26, 27, 28, 29, 30, 31, 32, 33. And then you got some more pieces here. I'll go 34 there, and then I'm a little afraid to touch some of these. I'll just go 35 here, and some of it is left over. I'll just call it even, and I don't want to risk it too much. So there's approximately 35-ish here, and I'm guessing it'll be the same over here, another 35-ish. So here's a method that you could use 4,000 years ago with no tools other than your common sense. You say, hey, this has approximately 70 square inches. 70 little squares. So if you took your pizza here, you should try it at home, just for fun. Take your 5-inch pizza, by the way, the pizza places will call it a 10-inch, because you go by diameter. Take your 10-inch diameter pizza and slice it up, and I bet you get approximately 70 of these little pieces. But of course, that's great if you were living 4,000 years ago. I'm sure that would woo women in the village. But nowadays, it doesn't impress people. What we require is, the human spirit is so much bigger than that. We're not about mediocrity. The human spirit demanded a better way to do it. We wanted to know, not roughly. This is roughly, look how many years you got. We wanted to know, not roughly, we wanted to know exactly how many square inches. So we want to know what's the area of the circle when you have radius r or radius 5 or whatever. And that required a big, bold, and brilliant idea. Nothing short of a big, they didn't require a little idea, no. A wicked, big idea. A bold and brilliant. By the way, this is exactly the spirit of mathematics. Mathematics is not about pushing numbers or doing things. Any old chump can do that. Mathematics, as many other things in life, are about big, bold, and brilliant ideas. Okay? Same thing with art, literature, all the great things about life. Many of the great things about life are making use of our brain to create or appreciate big, bold, brilliant ideas. Alright, enough of that. Let's get to the big, bold, and brilliant ideas. This was not good enough. We need something much, much bigger than that. So here's what people thought about a long, long, long time ago. You ready? You take some circle like this and you make a little dot in the center. There it is. Well, you say, well, that's not big or bold or brilliant. I agree with you. But relax. You're in good hands. I got your back. You take some scissors here. Boom, boom, boom. Scissors, and you cut it. Cut. You say, well, okay, that's not big, bold, or brilliant. Oh, wait, there's more. Once you've cut it from the outside to the center, you cut it again from the center towards the outside, but not all the way. And you do that a few times. How many times? A few. A few more than what you're thinking. More than that. Pick a number. More than that. You do it a lot of times. Many times. I don't want to scare you guys, but maybe infinite many times. If you got scared when I said that, skip that part. Just do it many times. And you say, well, okay, that's not brilliant, bold, but wait, there's more. What you do then is you grab this side, the one that you cut all the way through, the first one, and you split it open, and it would turn out to be more or less like a fan. Like this. This is the way it would turn out if you open it up. If I was to close this back in, it would look exactly like that. If I open it, it looks like this. Stop me from lying. You can't stop it. But wait, there's more. Let's look at some of the measurements here. How tall is this whole strip here? The tallness would come from the red lines in here, and each one of them would be r, the radius of the circle. Whatever r may be, that's how much each of these is, because they go all the way almost to the edge. So this r is the height of each of them. Well, you can't see that. This is r. Okay, let me see if I can squeeze it in here. R goes from here to here. And then the blue line would be the circumference all the way around. And we've talked about that in the last lecture. The circumference is equal to 2 pi r. Another timeless idea that comes from the definition of pi. So all the way around is 2 pi r. When you've opened it up, this becomes 2 pi r. 2 pi r. 2 pi r would be this distance from one side all the way up to the other side. And then you do the unthinkable. You do something bold and brilliant. You cut it again right there. You take your scissors and boom, you cut it right there. Why? Wait. I know, it would seem crazy to think why you do that, but until you see the brilliance of it, you won't know. You cut it, and then that would separate these two pieces. That would separate them into two different pieces. And then how big would each one be? The blue line. Well, the whole blue line was 2 pi r. Each of them would be just half of 2 pi r, which would just be, this one would be pi r, and this one would be pi r. So this, wait, there's more. Let's throw away these scissors. We don't need them anymore. Let's throw away this radius. We don't need it anymore. Let's throw away this. Let's move this over to the side. Let's move this over here. Let's move this here. Let's move this here. And then let's do something crazy here. We see this other piece. We're going to turn it around. Spin it. Come on. Come to Poppy. Spin. No. Yeah. Now spin a little more. Not too much. And then we're going to fit it into the holes of the other piece. Just like that. Nice and perfect. Now look what you've got. Well, you've got if this thing wasn't sticking there. You've got a perfect rectangle. A rectangle. Base times height. Everybody knows, or should know, that how to calculate the area for a rectangle. The area for a rectangle is base times height. Now what is the base for this rectangle? The base would be pi r. What would be the height? The height, we said, is r. Now wait a minute. Base times height. Pi r times r. How much is that? Pi times r times r. Whoa. Isn't that pi r square? See where they pay me? Insane amounts of money? Okay, that's exactly the timeless idea. idea, the timeless idea tells you that the area of a circle is equal to pi r squared. You may have heard of it. You know, Chunk has heard of it and memorized it, but to understand it, it requires a big, bold, and bright idea, just like this. And so we can go back to our approach of ideas from 4,000 years ago, and we can refine them. We now know that this is the radius is 5. We can, let me see, I'll do it. Let me delete some of this stuff so it's room for 10. So now the new approach after the big bold idea would be, hey, this area would be equal to, let's go with yellow. This area would be equal to pi times r squared. So that would be equal to pi times 5 squared. That's exact area, not approximate. No, this stuff, okay, it's good for 4,000 years. So this is the new millennium. It is exactly pi r squared. And you can get an even better approximation if you approximate the pi part. Let's see if we can do that here. Show you guys. See the light part. So you got the pi. Much better approximation would be 78.54 square inches. So if you were to, this provides a very, very elegant solution, not only an elegant solution to the original question, but it provides a formula that you can use on all possible circles. The area is equal to pi r square. Forever. This idea right here is beautiful today. This idea was beautiful 500 years ago. And 1,000 years from now, when we're all dead, this idea will still be a very beautiful idea. That right there, that's the spirit of mathematics. Alright, I digress. Let's try a formula on a couple of examples. Suppose you've got a circle with radius 12 inches. And suppose you want to know what the area is. So we use area is equal to pi r square. All you do is plug in there the radius, which is 12 inches squared. That gives you 144 times inches squared times pi. So I'll put the pi here times inches squared. So it's 144 pi inches squared. And again, if you wanted to approximate, you could plug in the calculator and get an approximate answer. That's not as interesting to me. I'll let you handle that. Run through another quick example. Suppose you've got a circle with radius 4. The area is equal to pi r square. All you do is do the pi times the r square. Whatever the units are, they would go in there. If this has no units, we'll leave those off for now. So this would be 16 pi. That's the exact area. If you wanted to approximate, you'd have to approximate that one and get your answer, approximate numerical value for that. Or you could just leave it exact as 16 pi. It's all good. Alright, carrying out those examples should be fairly routine. Let's take it up a notch or two. What would happen if you don't have a full circle? Could we get a formula for just a piece of the circle, a portion of it? Often these portions of circles are called sectors. For example, here, the implication is that we have exactly half the circle. And the question is, how would you find the area? You know, if this is 5 inches, and you wanted to cut this up into, let me see, you know, a bunch of little squares, so there's 5 of them, 1, 2, 3, 4, 5, and so on and so forth. How many would you get half, for half the circle? Well, the concept is really easy now that we've done the area for the whole circle. What you want to do is, or one way to do is to look at that is, what it is, it's half the entire circle, and so you say to yourself, you could say to yourself, the whole circle is pi r square. So that's equal to pi times 5 inches square. That would be equal to 25 pi inches square. That's the whole circle. Then you say to yourself, well, this is only a portion of it. A portion of it is half the entire area. So therefore, this would be a half of the entire area, which was 25 pi. There you go. That's how you would calculate it. Again, if you wanted an approximate answer, you could just plug that in there. I guess we could do that for fun. So it would be 0.5 times, let's go down to the bottom. 0.5 times 25 times pi is equal to whatever, then we change it. About 39. So it's approximately 39.27 square inches. That's how many little square inches you get from just the top of the pizza. That's 5 inches in radius. But it gets more interesting than that. Suppose you had a different sector, a different piece of it, not half like we did here, but suppose you had a quarter of it. Again, it would be very powerful to just look at it as a portion of the entire circle. So this was red. Area for the whole thing is pi r square. And then the white portion would be 1/4 of pi r square. Why? Because the implication is that you've got just 1/4 of the area. It's pretty easy, right? But it gets a little bit more interesting in that, suppose you had not 1/4 or 1/2, but some odd number of degrees. How would you do it? Like 60 degrees. Again, you would just look at it as a portion of the circle. We know that the area for the entire circle is pi r square. What would this be? What portion do we have just in this sector? Well, 60 degrees. What does that mean? How many degrees are there all the way around? All the way around there's 360. That was the definition of a degree, 360. Here we've got 60 out of the 360. So the portion that we have, that would be this area, would be 60 out of 360. That's the portion times the total area, which is pi r square. See how we do it? We just take the portion, just 60 over 360 times the pi r square. And whatever the r may be, you could plug it in if you had an actual example where you had numbers on it. But the principle is pretty easy, but it ends up into a famous formula. That's what I'm trying to get to. Here it is. Here's a famous formula for you. So if you have x number of radians, it's similar to this problem here, but this one was in degrees. Degrees, 60 out of 360 degrees. Radians is different. You gotta think, how many radians are there in the whole circle? Let me see. Well, half of it would be pi radians, and then the other half would be another pi radians. Remember that? Pi radians fit in half the top half of the circle, and pi fit on the bottom. So the whole circle has 2 pi radians. And so the portion of the circle would be, alright, so this is the same way. The entire area would be equal to pi r square. The portion that we have here is just a certain portion of that. I'll leave this for the fraction for the portion, and of course in here you have the whole thing pi r square. And the only question is, what portion do you have? You have x number of radians out of how many radians total? Think out of 2 pi. Remember, every pi can be changed for 180 degrees. So you have 360, you got 2 of them. That's the portion. Now the reason this becomes a famous formula is because it cleans up nicely. Let's call this the area of a sector. S for sector. No, that's bad. Let's call this, what should we call it? We shall call it, A with a little S for sector. So the area for the sector is equal, the reason it's famous is because this cleans up nicely. You see the pi here, cancels. This pi cancels with that one. And so what you're left with is a famous formula that goes like this. X over 2 times r square. That right there, that's super famous. Anytime you want to find the area of a sector, as long as you have the radians, if you have so many radians, x, all you do is x over 2 times r square. And this is the complete reason as to why you do that. These pi's cancel, all you're doing is taking a portion. It might look a little bit more complicated, but if you sit there and think about it, it's not more complicated than something as simple as this. That's why we did this at the beginning, because it's exactly 0, so the default is radians, over 2 times whatever the radius is, square. And that's it, you'd be done. If the radius was 5, you'd just put there 5 square, and that would be exactly the area. Applying this formula. The number of radians divided by 2 times the radius square. Super, super famous. I'm going to give it some color because it's so famous. Okay? Just threw that in there for free. Okay, and then you could play the same game with degrees. For the area, again, the area for the whole thing would be pi r square. That would be for the whole circle. The area for the sector would be a certain portion times your pi r square. What portion do we have? If x is given in degrees, the portion would be, you think, x degrees out of 360. That's the portion. This one doesn't clean up as nicely. That's why this one's not as famous as the one for radians. The one for radians cleans up nicely because, can't see it because I did all this stuff on it, but because the pi's cancel, this cleans up nicely. You don't even have pi, you just have the number of radians divided by 2. This one does not clean up as nicely. This number of degrees over 360 times pi r square. Okay, and this is for areas of sector. That's how many little squares are inside. It turns out you could play exactly the same game for arc lengths, for portions of the circumference. Alright, so let's try the same sort of principle on arc length. Suppose you want to know how long this blue portion is. It's part of the circumference of the circle. We've done this stuff before, but let me just make the analogy here. That we can look at it the same way we did for areas. First, what we do is we say, okay, the whole thing has circumference is equal to 2 pi r. So the blue portion right there, that would be, we call S for arc length. That would be a certain portion of the entire circle, which is 2 pi r. Now the only question is, what portion is this? Since it's 180 degrees, the portion is 180 out of 360, or you could say 1/2, either way. 1/2 or 360, or 180 over 360. Okay, and that would give you the right arc length. And of course you could put the r for whatever you want, if it's 5 inches or 5 miles. Really, that r part doesn't matter. All you do is just plug it in there. And of course, you know, pieces could be anything. For this 180 degrees, in the same way. You'd say, right, the whole thing has circumference is equal to 2 pi r. While the blue portion is just a certain portion of the entire circumference, which is 2 pi r. And then all you got to figure out what portion do you have here. And you could just say, well, it's 1/4 of the whole circle, or you could say it's 90 degrees out of 360, which of course could be reduced to 1/4. Either way, you get the correct result here. Applying exactly the same principle. You look at it as a portion of the whole circle. And then we want to see how that helps us come up with famous formulas. Let's try this one for, well, this one's given in radians. Let's try this one. So the whole thing, the whole circumference is equal to 2 pi r. Now the portion that we're talking about is just a certain portion of the entire circumference, which is 2 pi r. All we got to figure out what portion do we have here. Well, we have 1.2 radians, and the only question is how many radians all the way around. Remember we talked about 3.14 on the top, about 3.14 on the bottom, exactly pi on the top, pi on the bottom, exactly 2 pi radians all the way around the circle. So this is how much arc length it would be when it's given in radians. By the way, this again turns out into an incredibly famous statement, which can be seen by the following. You see this 2 cancels with that 2, and this pi cancels with that pi. It cleans up nicely where all you get is s is equal to 1.2 times your r that you have here. Because the 2 pi cancels with that, this one cancels with that, and it cleans up really, really nicely. In fact, you can turn that into a formula. You say if x is given in radians, the whole thing is 2 pi r. So then the blue portion, which is the arc length, would be a certain portion of the 2 pi r. And you think, well, which portion is it? Well, it's x radians, 2 pi r, it's x radians out of 2 pi radians total. This is the portion of the circle that you have. I know it may look more complicated, but it's not different than when we had 1/2 or 1/4. It's just x many radians out of a total of 2 pi. The reason this is famous is because it cleans up so nicely. Well, that's not the only reason, but one way to see it is because this cleans up nicely. The 2 pi cancels that 2 pi. Now you get is x times r. Super, super, super famous. I think this one we gotta give it some color because it's so famous. Put a little hand there pointing at it. The arc length of a piece of a circle here, the arc length is equal to the radius, or the radius r, that's this piece right here, r, times the number of radians. Okay? And if you think about it more deeply, this is a very, very simple statement that comes out of the definition of a radian. But I'll let you think about that. When you're ready, you will see it. Anyway, that's super, super famous. You can play the same game in degrees, but it doesn't clean up as nicely. The arc length would be given by x out of 360 times 2 pi r. You see, it doesn't clean up as nicely. You can clean it up maybe a little bit. The 2 cancels out, you get x out of 180. But you still got the pi r there. That's why it's clean as it'll get. So in degrees it's not as famous, but in radians it's super famous. And the principle for all of these is exactly the same. You just take the portion of the circle, multiply by the entire area or entire circumference, whatever it is that you're talking about. Okay? This commercial a long time ago. You can tell by the car there it's kind of aged. And I remember thinking, wow, that'd be interesting. I wonder how fast would you have to drive so that you can keep up with the sunset. As the sun sets, you keep driving so that you can keep up with it. How fast would you have to drive? And I always thought that would be interesting to figure out. And then the other thing I thought would be interesting is to put it actually in this class, because by now we have all the tools that we need to figure out that little curious question. So the idea is you take a look at the Earth here. It's approximately 3,963 miles in radius. And what we've got to do here is imagine the car right here. And maybe the sun is over here. The sun is shining. And the Earth is spinning. Spinning and spinning and spinning. So if it spins this way, the car's going to go down over here and you won't be able to see the sun anymore. So the car has to keep driving at the same rate that the Earth is spinning. So what I thought would be a good way to do it would be to figure out, well, how large is the circumference of the Earth? If the radius is equal to 3,963 miles, well then the whole thing, circumference would be 2 pi r. That would give you a grand total of, let's do a little calculator here, let's put a little light on it. See, I did it there before. 2 pi times the radius is about 24,900.26 miles. What does that mean? If you were to drive all the way around the Earth, that's about almost 25,000 miles. Or, said a different way, if your car, if you see on the speedometer or odometer says 100,000 miles, you probably could have gone around the Earth 4 times. So to go around the Earth, it takes about 25,000 miles. Anyways, what does that have to do with our problem? Well, how many, just to stay on top of the Earth, just to stay on top of it, how many miles would you have to drive every hour? One way to look at it is this way. The whole Earth will spin 24,900 miles in 24 hours. So every single hour, the amount of part of the circumference that's spinning, maybe you have to cut it into 24 pieces, 24 chunks to see how much it spins every hour. So I would take that 24,000 and divide it by 24. And the result is, so I take the circumference and I multiply times 124. That's the portion of the Earth that's being rotated every hour. And that would give me 1,037.51 miles. So in other words, if your car drove 1,037 miles every hour, you could afford to just stay on top of the Earth. Or, said differently, if you want to drive and keep up with the sunset, you would have to drive at exactly, or roughly, you would have to drive at roughly 1,037 miles per hour. Pretty interesting, huh? I'm gonna try one of these days. Alright, that's fun. We should call it a night. You guys gotta do the homework, read the notes, take a self-quiz if there is one available, and we'll see you guys next time. Peace.